Hey, thanks. Great to be back at GHU, like after 5 years. It's very interesting. So my talk will be about it will start in a very basic way, what are the fundamental concepts in this field that is currently called deep learning, like what are the neurons and weights, and basically mathematically how these concepts are represented. And then once I will explain what the depth in the models means, then I will go to the models that are successful in the NLP community right now, that are based usually on the recurrent networks. So I will describe the models, how do they work, and then currently a very popular topic that many people are very curious about, how it works with the longer short-term memory in these networks. There is this LSTM architecture that is very popular right now because many people use it as it's implemented in many toolkits. And I think it's great to understand what it really learns, and I will show even a simplification of it that can be used for the NLP tasks, while it's much easier to analyze what it actually learns. That's more like the current state of the art in the deep learning in NLP, I would say. So the last part of the talk will be about how can we go beyond the deep learning. I will show some architecture of some special recurrent neural network that can do things that the normal recurrent nets cannot do, and that will be more the motivating work for the future work. I think especially for the PhD students right now, how to discover some interesting new fundamental concepts for the future. So for the motivation, that's very simple. People are using neural networks often because they just want to get better applications, in the companies. Of course, techniques like logistic regression and support vector machines were very dominant because they are simple and scalable. And these days, people want to scale these techniques to do something more interesting, to be more precise, and are using for these tasks neural networks. I would say that especially for NLP, the situation is that we don't really have techniques or problems where the neural networks would work so much better than the previous techniques that there will be some huge gap. It's usually some small difference, but because in the competitions the victory goes to the best, it's always good to work on the best technique. So even if one can get only few % better speech equalizer, I think it's still worthwhile to consider these techniques, especially if one wants to win the competition. So to describe the neural networks and the deep learning, I will start from the basics, what the neuron is. I know that many people here already know this very well. I just think that the talks that make assumptions that everybody knows already everything are kind of boring, because then the people who actually don't know the basics will not understand anything. So I will start with the description that is very simple of what is a neuron, which is a basic computational unit in a neural network. It has some input synapses that bring the input signal that gets usually multiplied by some weights, which is exactly what we train. The weights are trained. Then there is some nonlinear activation function that takes some kind of sum of the weighted input signal, applied some non-linearity, and produces the output. So if we would look at it from the mathematical point of view, we can say that for some case of activation function, we can say that the output is something like max between 0 and the incoming signal multiplied by the weights. So now that we have this notion of the artificial neural network, I think it's always good to repeat that actually these artificial neurons are more like a computational units. They are not the same thing as the biological neurons. There is some similarity in the sense that biological neurons also get some inputs and produce a single output, but that's pretty much all the similarity, because almost everything else is different. Encoding of the information is more in the frequency domain in the biological neurons, while the artificial neurons usually encode the strength of the information by simply a larger value. And the learning is also quite a bit different. I don't think that there's any backpropagation going on in the brain. So there's actually quite a lot of differences. So I think it's good if people really make this distinction. And when we are talking about artificial neural networks, we are not really talking about how the brain works, but we are talking about the mathematical models. For the activation function that I mentioned before, it's actually a crucial part of the neural network. It's really important to understand it because it gives the neural network more power than the linear techniques like say logistic regression. We can have like many non-linearities. The two most frequent ones are the sigmoid, which is like shown here at the figure, and the other one is like the rectified linear unit, which is basically just the max between the zero and the value. So it's very simple. An example where we need the non-linearity is like this classic problem from like the 60s, the XOR problem from Minsky and Pepper's book called perceptrons, that actually was analyzing like limitations of some of the simple units and mathematical models that are based on these simple units called neural networks. So this problem basically is about like finding, say, a decision plane in this space where we have like two classes, like the blue circles and the red circles. And if we have a linear classifier, there's basically no linear separating plane that we can choose so that we would be able to make the classifier work. So if we have the activation function, then we can actually make some hidden neurons that will be activated just for some subset of the input space, and then the next layer can actually recombine the outputs of these neurons. So if we have the activation function, we can solve problems like this. Without the activation function, it's not doable. So because this talk is more like in the NLP side, so that there's an example here with like some kind of like very simple language. Let's say that we want to build just some binary classifier of like if for example the sentence is like having a positive or negative sentiment. That I think that's like pretty much the most trivial example that one can come up with. And if we want to detect, for example, that a bigram means something else than just the sum of the individual words, like for example that not bad is not the sum of not and bad, then we have to develop some functionality in the network that will be activated only for like this combination of words when they appear next to each other and not otherwise. So this kind of like Boolean features can be learned if the network has the nonlinearity. So this is basically the summary of what I just said, that we really need the activation function to give the models more representational power compared to more like shallow techniques. And if we don't have the activation function, then we cannot model the nonlinear functions. So this is basically where the hidden layer comes in, that usually learns some nonlinear combination of the input features from the previous layer, which can be the input layer or the previous hidden layer. And difference to like SVMs with the nonlinear kernels is that actually the features really get learned usually by stochastic gradient descent, SGD, and the backpropagation algorithms. That's like the key concepts that almost everybody is using these days. And there's the solution for the XOR problem. As I said, like we can have some neurons that will just be activated for some part of the input space. There's the frequent argument that actually people used to mention very frequently, like especially several years ago when they were somewhat rejecting the deep learning idea by saying that it was proven already that a neural network with one hidden layer is a universal approximator, which means that it can represent any function up to like any desired precision. So I think that it's actually very important to understand this argument to get the motivation for like the deep learning. And the argumentation goes that that not all the functions can be actually represented efficiently with a single hidden layer. So I will show more examples later, but really the efficiency is a key concept. So this is like just a graphical representation of how we can think of the input layers, hidden layers, and the output layers. Of course, you can have more hidden layers inside, but this is like a simple model with one hidden layer. But there are some activation functions in the output layer. We can have, for example, a classifier that gives us probability distribution, for example, of the next word if we have a language model. And the deep learning is really like about having more computational steps, more hidden layers in the model. And that's basically the definition of the deep architecture. The deep architecture is some architecture that involves more of these non-linearities to be consecutively applied after each other. Deep learning then aims to learn patterns that cannot be learned efficiently with shallow models, which I think is a little bit tricky because it's usually like something that we show empirically. It's much harder to prove it, that there doesn't exist any shallow model that can learn the patterns that we usually learn with the deep networks. Also, like because of the universal approximate argument, once we actually learn some deep architecture so that it actually discovers some complex patterns, we can actually make something like a lookup table that will pre-compute all the results that this model was able to learn, and it will learn like a lookup table for all possible inputs. It will learn all the outputs, and the resulting model will be very shallow. So I think that these concepts are actually not easy to understand, and right now in the community, I think there's a lot of mystification about what the deep learning actually is and what it's not, and it's often getting renamed. I've heard even like some people arguing that PCA can be said that it's deep learning, which I think is definitely not. But different people have different opinions, even if the term was defined quite precisely like 6-7 years ago. So back to the argument with the universal approximator. Why would we need more hidden layers? We can actually have a lookup table that will be able to approximate any function, as like shown here. Like we can think of like sampling more and more points in the input space, and just with single hidden layer, we can have like a neuron just that will be activated for like some small subset of the input space, and the output will be basically just the value as in a lookup table, and we can make like this hidden layer bigger and bigger and make the approximation more precise. So the reason why we can't really do this is that we will not be able to obtain generalization. We usually don't have infinite amounts of training data, and the same argument as goes with n-grams. Like if you want to build a language model based on n-grams, if you have infinite amounts of data and infinite n for n-grams, then it can actually also like kind of describe all the patterns. I think it was Shannon's argument in the 50s. The point is that we never have actually infinite amounts of data. So if we will have finite amounts of data, then we actually care about like learning as much as we can from a limited amount of data. And then if we can represent some patterns with like efficient architecture, that maybe will have more depth, but it will have much smaller width, so that the layers will be much smaller, but there will be several of them. If we can learn these architectures, we can expect them to generalize much better, which actually for some problems does happen. For example, for vision or speech, the deep models are now normally used. So, as I just said, like there are some functions where we wouldn't need exponentially many hidden units with increasing the size of the input layer. Like one kind of famous example, also like from the perceptrons book, is the parity function. If we have n bits at the input and the output is supposed to be 1, when the number of active input bits is odd, then we can't really represent the parity function efficiently with just one hidden layer. While if we would have more hidden layers, then the number of parameters that we need to represent this function is much smaller. And it turns out that even if we want to train a neural network that will be able to like recognize this pattern, it's doable if we have more hidden layers. While with single hidden layer, we really need to see all possible combinations at the input. So the network will really just do memorization. It will not really be able to generalize. And another example can be like addition of two numbers, where we can really think of like building, for example, a calculator that would have a huge lookup table. If you, for example, want to add two numbers that have up to 3 digits, then there's like finite number of combinations that you can see. You can think of building a calculator that sees all the possible combinations of the input numbers in a lookup table and just produces the result without doing any computation. But the normal calculators that we are using these days are constructed differently. They usually compute the result because once you go to very large numbers, it basically becomes inefficient to use the lookup table, and we can just use more like a deep system that does the computation and is much more efficient. So, as I said, having hidden layers exponentially larger than necessary is bad, because we will need also like much more training examples, and then we will not really generalize. So that's the whole point of deep learning, having models that can compactly represent some complex patterns by probably doing some more computation, and then using less parameters, so they can be actually trained to perform better and generalize better with the same amount of the training data as the shallow techniques. So this is just the graphical representation. How would it look like? Basically, like the output from the hidden layer is the input for the hidden layer number 2, and so on. So nothing really special. Still like the same functions as before. Historically, there were like many books when I was a student. Like I did read a lot of like these tutorials on the neural networks, and the books that were claiming that even if these theoretical arguments are known from the 60s, that it should be possible to like learn something like more complex using more hidden layers. It's not possible to achieve this by stochastic gradient descent and backpropagation. So people did focus for a long time on trying to develop like more complicated techniques that would be possibly able to succeed here. But it turned out that basically it wasn't much the fault of the techniques as it was of the tasks that people were using. It was usually some very small data sets. And in the last 5 years, the big difference is that people are now using huge amounts of training data. And for some tasks where the signals are very compositional, like for speech and vision, the deep learning just works as it is, which means that we can have just the usual neural network and maybe a few tricks there, but nothing really special. And it will just rely on really like a hierarchy of features, for example, for the vision problems and so on. I think pretty much everybody must have seen that already, like the results that people are showing like on ImageNet, that they can classify the objects and so on. It performs amazingly well. And it's similar for the speech recognition, like there are these acoustic models based on the deep networks. I think that's pretty amazing, but in the end it turned out that it wasn't really like because of better techniques, but more this breakthrough was more caused by, in my opinion, by the different tasks and training sets. Still, I would say that deep learning is definitely an open research problem if we would really see it in the broad context. Like, how do we learn some computational mechanisms that really are non-trivial, like not shallow? There were like there were proposed many deep models or deep architectures that unfortunately do not really learn anything else than what the shallow models would learn. I think this is actually especially true for the NLP community, that people get sometimes, I don't know, like it's of course very individual, but there was a lot of results that were overhyped, that people were very excited about their own results, and they did publish a data set together with a new technique with claims that the technique is state of the art, even if nobody else was working on the data set before, because it was a new data set, and then it was associated with the deep learning. While later, when people did try actually the well-tuned shallow learning techniques, which is like more like the traditional ones, like say using back of words or back of engrams representation of the sentences, and then some classifier like the support vector machine logistic segregation on top of it. Usually, it wasn't really like some clear victory there. It seems that the classic techniques are actually very competitive often, and if they don't have to be trained, or like very little has to be trained there, they can be also more efficient. So it's it's really, as I'm writing here, like it's still an open research problem, especially for NLP. And I think people should still think of it like, how do we learn more complex patterns in the language? I think that should be like the question for us. Something that, in my opinion, still works is what I was doing here, like at CLSP in 2010, which is the recurrent neural network language model. There, as far as I know, no shallow techniques or a combination of shallow techniques can match the performance of the best recurrent neural networks, and the difference is pretty huge. If I remember the results correctly, like on the Penn Treebank, that was quite popular data set here at GHU, the best Engram models were around like 141 perplexity, and the best combination of the traditional techniques, which was like class-based models, random forest, structured models, and so on, that it go to maybe like 110. And with the best recurrent networks combined with everything else, in my thesis I did publish like a number like 72, which is like way better. And last year it was published even better number with some huge number of really huge LSTM models, which did go to like perplexity 68. So I think that there's really like a big difference between like 70 and 110. So the difference is really big. And even if the Penn Treebank is small, like we did observe similar difference even on larger data sets. Like at Google, we did publish a data set called 1 billion word benchmark. And there we published also like very strong results with the recurrent network language models. So I think that people can try it, especially if they believe that they can beat these numbers with the shallow techniques. I'm not sure if it's doable, but definitely the feed-forward neural network language models, which were here like before, are going to be not that far from the recurrent networks. So I wouldn't say that the recurrent networks are like some big victory compared to like more shallow models that have actually non-linearities, like the neural nets. But still, it's the state of the art right now. So here is the figure that kind of should explain how the model works like. It's actually very simple. The architecture is known as Elman network because Jeff Elman was using models with this architecture in the 1991 or maybe 1990, and it was like very famous because it's very simple, intuitive, and interesting, and the training is quite different than what Jeff Elman was using. But again, it's like the same story as before, like SGD and backpropagation. In context of recurrent networks, it's called backpropagation through time, which means that we unfold a network that has these recurrent connections in time, which means that it becomes some kind of like deep network with shared weights. It's more like a details. The basic equations like are very simple. We have like some input layer that encodes the incoming words. Then we have a hidden layer that has the nonlinear neurons. And then we have the output layer, which is like the prediction of the next word. So it represents the softmax or the probability distribution over the next word. And then we have the recurrence, which gives the model the ability to form some kind of short-term memory. Because the hidden layer is basically connected to itself through some time-delayed connections, which means that the output of the hidden layer in the previous time step can be seen as the input features for the hidden layer in the current time. And I think that's pretty much all to say about like how the model works. The training would be a little bit more complicated, but as I said, like that's what I have described in the papers. And what I think it's more interesting to say as some new thing, there was like in the last few years a lot of extensions that aim to give this model the ability to have some kind of longer short-term memory. Like as I was saying here in the figure, the model actually has the ability to form the short-term memory because it creates it in the state of the hidden layer that gets copied across time steps, or copied like it's like as the features for the future time steps. So it creates the short-term memory in the state of the hidden layer. The outputs of the neurons are basically the memory, but they are like these well-known problems that were described, I think, by Seb Hochreiter in 1991 and later by Yoshio Benji, like about the vanishing gradients. which means that this architecture will tend to forget the long-term information and will focus mostly just on the recent information, because that's more important for the immediate prediction. So the dynamics that the network will tend to form will favor the short-term information. And so people were trying to overcome this problem by developing different architectures and different techniques. In my opinion, the different techniques, again, didn't really work as well as promised. So still what works these days is just SGD. And what changed to allow more of the memory in the network, or longer memory, is the difference in the architecture. So we can say that actually learning the longer memory in language modeling in general was definitely doable, even like in the already like since 90s, like people were using these models called cache models, which were essentially the longer memory, like a bag of words, for example, last 100 words that is interpolated with the probabilities given by the n-grams. And that was actually like known for a very long time that even if the model is trivial, it can actually help. And later, as I will be describing how the longer memory in the recurrent networks works, I think it should become obvious that it's actually very related to the cache models. So to describe the architectural changes that we'll have to make, there is this figure of a neuron that is connected just to itself. So like through some time-delayed connection shown here. So it's different than the Elman network in the sense that in Elman network, the state of the hidden layer was seen as input features for the next state of the hidden layer in the next time step. Here, the neurons are connected only to themselves. So instead of having this full weight matrix where all the neurons in the hidden layer are connected to all the future neurons in the next time step of the hidden layer, here the weight matrix can be seen as a diagonal in a sense that the neuron is connected just to itself and it doesn't see the states of the other neurons. There was actually an architecture of a recurrent network that it used these neurons that were just connected to themselves. It was developed, I think, in the 80s. There were, I think, at least two people working on it, Mike Jordan and Mike Moser. And so it's not really something new, like the idea is definitely old. So what we tried to do recently is to combine basically both of these things together. So we can have like the Elman architecture, which is like the fully connected recurrent layer, which is on this picture denoted as the HT with the full matrix R. And then we can have the kind of like slowly changing longer short-term memory that is based on like the Moser architecture, where the neurons are connected just to themselves by some with some parameter, which is like the weight of the self-connection, which is close to 1, so that the neurons tend to keep their state the same. And so it can be seen basically as a connection of the Elman and Moser architectures. And because we can show that it can be seen as just a normal RNN with some structural constraint on the weight matrix, basically partially diagonal hidden layer, we call this architecture further structurally constrained recurrent network. We'll show a few results. We have much more results in a paper here. We published this year at iClear workshop. Here's the LSTM that we will be comparing it against, because this is a very popular model. I will not describe it in detail, but it's another architecture that allows to learn this longer short-term memory, and many people are using it now, in my opinion, without really understanding what is happening there. Of course, some people do understand what the model does, but I think still majority of the users take it as a black box and don't really know where the longer memory is coming from. So the model basically works as that there is some neuron with 3 gates. There is input gate and forget gate and output gate that allows basically the signal to be switched off, so that the gradients wouldn't flow through this computational unit, which is definitely much more complicated than a normal neuron. So it's quite a complicated model that many people believe can be can be simplified, which I think that the one that I was describing before is actually aiming exactly on this, to make something simpler. Here are just a few results. I don't have many results in the presentation, but just to show that there is some empirical evidence that what I was trying to achieve may be actually happening. So there's like a perplexity in this Penn Treebank with Ngram model and Ngram model plus cache that gives like a reduction by like 16 points, like going from 141 to 125. So definitely cache helps. And if we have RNN with 100 hidden units and we add to it like 40 of these slow units, like these only self-connected neurons, then we get like 215, which is like 14 points slower. So it's very similar again as from the cache model, and we have a lot of empirical evidence that it really learns this longer memory. And then the LSTM is pretty much the same story. We did get the same results. Like it's very close to like the best numbers that we can get. So the models are not kept like artificially small for any reason. Like even if the numbers can get a little bit better, it's not really like any difference in the story. So it seems that really like both the LSTM and this structurally constrained recurrent network learns something like a cache from like the language data, and then the main advantage of the model that I was describing at the beginning, with like this like usual hidden layer and this like slowly changing hidden layer, is that this model is much smaller. It has much more parameters than the LSTM that have the complicated units that I was showing just in the previous slide. So it's faster to train the simpler model, and in my opinion, it's especially good that it's much easier to understand it. So even when people train the LSTM, they actually know what to expect from it. Like I think, for example, when people are applying LSTMs to tasks where they try to predict very short sequences, for example, generate a caption of an image that on average is like 4 or 5 words long, then once we understand that the LSTM is really like a cache recurrent neural network, then it doesn't really make sense to use the cache, because the history is so short that there will be no difference. So that was more like for what I think is the current state of the art in the NLP with the deep learning techniques. Of course, other people would have different opinions, but in my personal opinion, the other techniques that people are like selling these days as deep learning for NLP, it's not really clear if there is such like a big difference or any difference to shallow techniques. So I would say that there is some success with the recurrent networks, but we should be definitely thinking about like what to do next, because it seems that just applying what already has been done to like new data sets and training models faster with bigger hidden layers and more data and so on, like I'm a little bit pessimistic about like if we can obtain some breakthrough just by applying what we already know, and maybe it's time to do something new. I feel that if we are limited to like the current data sets and tasks, we may end up doing research that is not really novel. It's very difficult to beat the state-of-the-art results, and developing new techniques that will be working immediately well on like some well-established data sets, for example, for speech recognition, may be just too hard. So maybe we should just develop new data sets. And for that, I think that the new data sets should be something that would be more ambitious and like much more like fun from the research point of view. Like, for example, in my opinion, we don't have tasks that would be about like some real language understanding on the level of like what humans have. Like, definitely the big part of human language is that we are able to communicate with each other, transfer information, and learn from each other. And I feel that we don't really have tasks that would be much about the learning and communication in language. There's definitely a lot of tasks that are about the knowledge, where, for example, one can compose a large data set that is, for example, about question answering, where the goal is for the model to know as much as possible. I think that the AI research should be more about like not knowing everything possible, but about being able to actually acquire information, being able to learn. So if you don't know, for example, what's the capital city of Germany, I think that's completely fine. But if we will talk to each other and you will hear like what is the answer, and you cannot use it in the future, then there's definitely like some problem with the intelligence. So I think that's exactly the state of the art right now. For example, with the statistical chatbots that do not have any history of the conversation, they cannot form the longer term memory, and not the short term memory, but really like long term memory, and then they are kind of like dumped in the conversation. So I think that the future should aim on like redefining the tasks and trying to do something new. So in my opinion, we need to develop both these things together. We have to try to develop better machine learning techniques, but at the same time, novel data sets, and it should be really tied together. I will show a few examples at the end of the presentation, but very, very simple ones. One way how to approach this is to think of what recurrent networks that I was showing before cannot model efficiently, because there was basically the whole motivation of these activation functions and more hidden layers, like to come up with some architecture that can model efficiently some patterns that the previous architectures couldn't model. So we can think of the recurrent networks, what they cannot do. Actually, there are very simple things that recurrent networks cannot do. For example, memorization of a variable length sequence of symbols. Like if you have, for example, a sentence and you want to remember it and then repeat the sentence, like I'm not saying that humans have infinite memory, definitely not, but we understand this concept of memorization. We can think of it, we can use it, and if we have a pen and a paper, we can actually solve like many tasks like this up to very large lengths. If we have a fixed size recurrent network that cannot develop any growing structure like a long-term memory, then of course it's like hopeless to capture this pattern, because it's basically not in the search space. So we call these patterns algorithmic patterns, and some like very basic examples from computer science are like the ANBN examples, where it's known, for example, that Feinstein machines cannot capture this pattern, while the I think context-free grammars can already do it, but then we can complicate the pattern a little bit, and we have to increase the power of the computational system and so on. But then there are like others, like sequence memorization that I was talking about, or even like addition of numbers. If you think that you have like a large set of some algebraic problems where you are supposed to like break the result of like addition of two numbers. With RNNs, you can of course memorize the results, as the lookup table calculator that I was describing earlier in this talk can work, but it cannot really like figure out the logic, because it's not in the search space. So we did develop this simple extension of the recurrent network that somewhat can actually learn some of these complicated things. We call it like augmented recurrent network, because essentially it's like a recurrent network that can learn how to operate stacks. On this picture there is a single one, but we actually did use usually something like 10 stacks during the trainings, so that there will be like wider search space. And this model can actually learn some complex patterns in sequential data, like what I was describing. I will just show results in a while. And it can learn how to construct and operate the long-term memory, even if it's like very limited, and it's just like, I would say, like the first steps in this direction. It's already like looking interesting, and potentially there's unlimited capacity in the sense that really it's not bounded by the size of the hidden layer, because it can learn how to grow the size of the memory, because the memory is represented by the stacks here. And we actually published the code as well, just somebody wants to try this model later. So here are like the results. There are like some very simple patterns that actually any machine that can count can recognize, like the ANBN, ANBN-CN, and so on, shown above. So actually LSTM works there, because LSTM has this capacity to form this mechanism how to linearly add some constant or subtract the constant, so it can actually learn to count. But we can just make a small modification to these problems, and instead of like asking it to count, if we just ask to memorize a sequence of, for example, some binary digits, then the LSTM already breaks, as is shown on the figure on the bottom left, the memorization patterns, where basically if we train the LSTM on like examples of memorization of the sequences up to some length, and then we test it on larger lengths, because it cannot represent the concept of memorization. Of course, it will not generalize, and then the stack RNN actually generalizes pretty well. And then we tried quite a bit more complicated problem, which is like binary addition. I will show it in detail on the next slide. And it seems that the stack RNN can still generalize pretty well, which actually was quite surprising to me. Armand did spend a lot of time with the first author on the paper, and I didn't believe that it can work, but in the end it did. And yeah.
So when you say RNN 10 plus 40, that means the hidden layer is 40 units and there are 10 stacks?
Stack RNN 40 plus 10 means that there's 40 hidden units and 10 stacks, yeah.
10 stacks.
Yeah.
And so the actions would have to be like in a set of 10 actions, not on each stack.
Yeah, you have to decide on an action on every stack. There is basically the basic operation with the stacks, like you can push some value, but you also have to learn what value to push, or you can pop the value from the top of the stack, or you can decide to do no operation so that you will just do nothing. I think it will be a little bit more clear here, basically, where we are showing what the stacks actually did learn on the most complicated problem that we did try, like this binary addition, where you can imagine that there is some input data coming in as a stream of basically symbols, like as in language model, and there you have like some number written there, then second number, and then you have like the result, which is like their addition, which is actually written in the friendly format for the stacks, like in the reverse order, because otherwise we would have to learn also like how many computational steps with the stacks you have to do before you can start predicting symbols, which would be quite complicated. So this is still like a simple problem or doable problem for the stacks, and here is like the functionality that the stacks did learn. So we did use 10 of them, and here we tried to like annotate it like what functionality we think different stacks did learn to have. So there was no supervised information; it's all learned unsupervisedly. So we don't give any targets what the stacks should be doing. We just did produce a lot of like these examples of these like complex patterns that represent some calculation, and then we did see that that some of the stacks have redundancy. Like, of course, there is no motivation for the networks to actually find a minimum solution. They can just have the information redundant across like several stacks if they just consider it useful. So they just learn to store the numbers. It's actually interesting to see that, for example, the number, the information about the number can be stored using completely different values than what was in the original number. Like here, it's stored like as a reverse, because it's actually irrelevant for the network, because it just needs to know the information. It doesn't really like just memorize exactly what was the input number. It just learns how to form the memory. That's the same for the second number. It also like learns to store it. And then after there is this equal sign, it starts predicting what will be the result, and it actually does it correctly. And that's what the previous figure was showing, like across many examples, a bit increasing length of these calculations. What is the accuracy? So it's still looking pretty good. And then it, of course, had to develop like this carryover mechanism so that it would be able to do the computation. So there's actually quite a few things that the stacks have to do, and how they have to be synchronized. And the interesting thing is that this was all learned still by SGD, like stochastic gradient descent, which I actually think is going to hit the limits soon, because there's, of course, this problem with the local minima, that once the stacks decide on some functionality, it's difficult to like move them to some different regime. Also, like the stacks are represented basically again like as some structurally constrained recurrent network, as I was describing before, like that the neurons were connected just to each other. We can see that we can have a weight matrix that would allow the values from the like diagonal to be copied one one step up or one step down, and that's actually how we represent the stack. So it's actually in the functionality very much related to the previous things, previous model. So to summarize this part, I would say that the RNNs that are like augmented with some data structure that is capable of growing can represent more complex patterns than the plain RNN. They can actually represent like general computation, like from the computer science. Like once we have two stacks, we can actually simulate a tape, and with the tape we have a machine that is like Turing complete in some sense. But of course, that doesn't mean that we can do just all the computation with just the model that I was showing. Like we would have to also learn how many steps do we have to do of the computation before we produce the result. But I would say that's a little bit secondary because we don't actually want to build a Turing machine, because that's not an efficient model of computation. The current computers are more like based on the idea that there is some random access memory and still with some topology. So I think that's more like for the future work. As I was saying just in the previous slide, we did succeed with training the model with SGD, but we also added a few simple things that are based more like on the search strategies, like when the model converges to some solution, we can still try to train many other models and see which model actually did converge to the best local minimum and use that one. So that's like a very simple search, but we can come up with a little bit more complicated search strategies. There is also like the same network can be trained completely with search, because as I was showing, like the number of neurons that we need can be actually very small. Actually, we need just much less than 40 neurons. Like I think that the binary addition can be solved like with just a few neurons, and then we can use even like exhaustive search strategies and incremental search strategies like beam search and so on. So many of these things can learn like interesting computations and interesting patterns in the data. So for me, the summary is that there are definitely like very interesting patterns that we can be still aiming for to learn and to develop machine learning techniques that can even represent them, which we don't really have these days. And in natural language, I think that this is exactly what we will need, something or some machine that can form a real long-term memory, that it can relearn how it should be structured. And that's basically something that we would need if we want to build, for example, chatbots that would be able to really like track the conversation and to remember what was said. So as for the conclusion, I would say that the basic concepts in artificial neural networks are very simple, but as we did see, like there's a lot of things that get more difficult later. When it comes to deep learning, there's many overstated claims. I would say that deep learning for NLP doesn't really do anything special yet. We have like some small success with the recurrent networks, but no big success that we will be able to do something that the shallow techniques do not do at all. So maybe in the future, for example, if we can come up with some language problems, even simpler ones, that would require the computation of the type that I was showing just before, then we can have some success, but that would mean that we would have to define new tasks. And that's maybe just what we should do, like define new tasks so that we can develop new techniques. So that's the conclusion of my talk. Thanks for the attention.
Thank you for the talk. My background is high-performance computing, so my question is biased towards hardware. What are the requirements on like the platform that you run on? Like, do you care whether you run on like a specialized GPU versus a high-performance processor for general science versus the cloud versus your desktop? What's your bias about the platform?
Well, I would say that I am personally not as biased as many other people are, because if you want to develop like a technique that will be like useful in production, of course you care about the speed a lot and you want to train it on as much data as you can. So there's a lot of people in companies that work exactly on this, like trying to figure out what is the best strategy. I did hear many like strong opinions from other people. For me, I would say that I'm fine with anything that works right now, and like the popular way how to train the vision models in the last years is to use the GPUs because they are kind of like cheap. I think that even like the distributed training is like very interesting, but it turned out to be quite complex to make it work. Like if you really have like a large network of thousands of computers that are kind of like slow, like it really seems like a very exciting problem to work on, but in the end it can become like kind of a nightmare. So in my opinion, this is harder to do. And of course, if you can have some supercomputer that has a lot of CPUs and big shared memory, then everything can get actually much easier. So for me, like I usually choose the simpler things that just require less work.
Two questions. Have you run this sentence analysis?
I did try on some of the data sets, but all of them are kind of toyish, like they are very small, and the performance that you can get there, like with some kind of like deep techniques or shallow techniques, it's pretty much all the same. So I did work on a few sentimental studies data sets. Do you have a question on some particular one?
Yeah, one of the questions or one of the slides you mentioned accuracy. I think no matter whether you are one layer or another layer, with the shadow,
Yeah.
really your model accuracy is the key.
Yeah, exactly.
So let's say if you build a classifier out of the your model,
Yeah.
or some analysis, you
Yeah.
need to figure out what's the accuracy.
Exactly, like
Predicting.
that's what I was trying to say at that slice. Like you can definitely create a deep architecture. There's no problem by adding more hidden layers. That's very easy. But if you want to say that you are actually doing deep learning, then you should show that you actually were able to learn something that the shallow network techniques did not learn. And how can you show it? Pretty much, it's very difficult to prove it mathematically, but you can show it empirically by showing what's the accuracy on some data set with the shallow technique, what's the accuracy with the deep technique. Then there's the danger that you will spend much more time by optimizing your deep technique, so you'll actually see some difference, even if there is no difference, but that basically happens all the time.
Yeah, that's a good reference. If you run time series, you will have accuracy built in. So it's a good reference. You can build your NLP. What would the accuracy be? Versus just run a time or a neural network from time series.
So I was more convinced myself, for example, by the recurrent networks and the language modeling, because there I was comparing the results to whatever people did develop in the last 15 years on the same data set. So I think that was much more convincing that, than if I would, for example, create my own sentiment analysis data set with like 10,000 training examples and then make some claims about it. I think that there is some example for me where the deep learning wasn't really as successful as it was sold originally for NLP. Sorry?
Not as successful?
Not as successful, yeah, because too small data sets and no strong baseline.
So during the discussion of LSTM and are you talking about how these models are potential and
For NLP applications, the patterns that are like called this longer shorter memory are definitely like very related to like some kind of like weighted learned cache model.
so have you done much visualization of that, or like how have you gotten your intuition?
Well, we did, of course, like run the experiment, so we like know pretty well what's happening there. You don't really need visualization. I don't think that we did any visualization, but you can, like there's a lot of things that you can do. If you want to actually see something, you can, for example, generate text from these models, and you would see that, for example, normal RNN has this problem that once you generate the text, it often jumps between the topics. If you generate text from these models that have the longer short-term memory, then they can actually like stay more focused on the topic. So like that's more like observation, like by just looking at it. Of course, you can more believe the numbers, and you can do experiment. I think we had it in the paper, or maybe we didn't put it there. I don't know, but we definitely made an experiment where you would take say data set where you know that the sentence order is important. For example, say Wikipedia, because then the sentences are correlated strongly, and that's going to help you if you have this longer memory. And then if you shuffle the sentence order, you can see how much you lose in the performance with the normal RNN, which is going to be like few points because they don't really form the longer memory. But you lose much more on these cache models because they suddenly get much less information from longer context.
Thanks for a nice talk. So I'm trying to understand your static RNNs. So it seems like the memory cells in LSTMs, you can view the input and output gates. It's kind of like a hot first kind of similar to clock switches.
Actually,
So how come there's such
there's a big difference in there's no topology in the LSTM. So sure, LSTM can do a lot of things, but consider the basic problem that I was showing there as the memorization of a sequence of symbols. So like LSTM has no mechanism how to, for example, create the neurons. It's not there. It's basically a fixed size model. It cannot grow. But if you have this recurrent network that can operate on some kind of like data structure, that can be still seen as kind of part of the model. But there you can like do this push operation, like say 1,000 times or 1,000,000 times in theory, and like put there a lot of information. So you have basically this growing mechanism, and that's the key difference. Like you don't have it at all in LSTM. So you can think even like of the human brain, something like a structure that kind of grows in time, in your lifetime, and maybe the growth is actually very important. Like the process that forms the structure, it might be actually much more important than people that assume, especially the people from the artificial neural network community, who usually assume that the structure, the topology is already given. It's not very important. You just have big layers everywhere, and that's it. But if you do not allow this growth, then you can't really model these concepts like memorization and so on. Even if there's enough parameters in the model to actually remember, say, 1,000,000 symbols, you can have a million hidden units in the model. But it'll be the same as with the parity problem. You will need to see all that number of training examples because it cannot actually capture the essence of the problem. Like it cannot represent the computation.
Consider implementing any other data structures?
Yeah, we tried a few of them. Like in the paper, I think we have the stacks and the list. Also, like the tape is a small modification where you can see that you have basically the tape capability once you have 2 stacks. Then I don't think we tried more of them. These are like the basic ones for computer science. You can think even about more complicated ones. But we have actually a lot of ideas there that we didn't publish yet, and maybe we will, so maybe I shouldn't talk about it. But basically, it's ongoing work.
Let's thank our speaker once again.